Okay. Yep, we're rolling. So first off, we're going to talk about advanced electron configuration. So electrons are pretty tricky things. They do many very different varieties, but the diagram that we gave you, which was is probably, we had the 2 in the first shell and then the 8 in the second, and then we had this problem in the third with these 18 electrons. So we're going to envision today, or we're going to show you what we mean by that problem with that third electron shell. So each of these shells have, in fact, within them what we would call subshells. All right, so we have an S subshell, which holds 2 electrons. We have a P subshell, which holds 6 electrons. We have a D subshell that holds 10, and we have an F subshell that holds 14. And they're up on the board there. You can see there, so you can copy them down later. So when we look at, say, like the first shell, it has 2 electrons, so it can't have a P, D, or F. Doesn't make sense, does it? It only has an S shell, and it holds 2 electrons. And we denote this, and if we're thinking really, we're talking about hydrogen and helium, or these 2 elements. And if you notice as we go across, we go 1, 2, we've filled that first shell. 1, 2, 3, 4, 5, 6, 7, 8, we've filled that second shell. So I would say that if I was going to name this element, it would be number 1, S, and first electron. So first shell in the S subshell, it's the first electron. So I would call it 1s1. You've got that sheet that you can fill in yourself. Yeah, you with me? So we look over here. This is going to be in the first shell still, S, and it's going to be that second electron. So we would call it 1s2. And that, of course, is our first shell filled up. So if we go down to the next layer, we've got 8 electrons. And so we would have, shut the door. We would have, thanks, brother. We would have 2 in the S shell, and we would have 6 in the P shell, and that would give us our 8. I know, it's not very, I wasn't a very good actor. Sorry about that. That's shh. So this is the second shell in the S shell, and it's the first electron. So the next one, of course, is going to be the second shell, S subshell, second electron. Now, remember, an S shell can only hold 2. So this over here would then be still our second shell, but we're now entering into the P subshell, and that would be the first electron, and we would call that 2p1. So, any guesses in pantomime of what we would call the next one? Yes, well done, 2p2. Okay, and we can continue to go across 2p3, 2p4, 2p5, and of course 2p6. Now we get to our third shell. And, well, once again over here we've got third shell, S subshell, first electron. Third shell, S subshell, second electron. And then, of course, we jump over here and we're going to go 3D1, 3D2, 3D3, P, what am I doing? 3P1, 3P2, 3P3, 3P4, 3P5, and 3P6. This is getting a bit ahead of myself then. It's the pantomime acting. It's going straight to my head. So then we'd say, well, hang on, there's 18. And as we said, we talked about this in class, that you fill up that octet. And then actually elements will jump down and fill in this 4s subshell first. So 4s1 and 4s2. And then, of course, where are the other 10? Well, they're in the middle here. So this would be what we would call 3D1, 3D2, and all the way over here till we get to 3D10. Yeah, you notice I just drew a line to 3D10. You fill them all in if you wish, though, especially if you're very dedicated. So what's this then? Well, this is still now the fourth shell, and it's 4p1. And this is one of the things kids find difficult. They find difficult that it starts at 2, but it can't start at 1. It's only got 2 electrons in it. So the p shell starts at 2, and then that this d sits in the middle, in between, say, the 4s and the 4p. Now, of course, if we continue on looking at this section here, the S section, well, we'll see that we'll get 5s, we'll get 6s, and we'll get 7s. And, of course, that'll be 1, 1, 1. So if we look at a bigger version of the periodic table, something along the lines of this, which doesn't quite fit. That's all right, it does now. If we look at a bigger version, this here are all our S shells. All right? In the middle here, these 10 are all our D shells. Now, you can mark this on your periodic table, but I wouldn't let you take something like that in. Okay, but you could mark it the way I'm marking it. These, of course, are what here? Yes, well done, the P shells. And these, of course, down the bottom here are our F shells. And so the advanced configuration probably makes the table make a little bit more sense. And of course, there's always that lonely warrior over here of poor old helium, which should be over here, but isn't, because, of course, it's a noble metal and non-reactive. So we turn to some of our questions. On our worksheet, on the back of the one that you're currently writing on, dude, in front of you. Yeah, okay, good. So it says determine what element is denoted by the following configuration. So starting at hydrogen, you go 1s2, so you go through both of them, yep. And you're going to end up at 3p4. So where is 3p4? That's S, yep. So the element that we're looking at, yeah. Here is 2p, 3p, 1, 2, 3, 4. So the element we're looking for is sulfur. And we just write that at it. So if I'm going to test you on this, which I am, I would give you that particular type of question. Now, if you wanted to, I'd be quite happy for you to put 2p, 3p like that. Are you with me? Just so you don't get confused about. So there, just that 2p and 3p, like on the television. Is it on television? It's not on television. Okay, that's kind of why I use this. All right, I'll put it on there. That's massively ironic. Yeah, it's still recording. Yeah. Okay, so the next question asks us to find 3d5. So what element is 3d5 plus all the others? So 3d5, well, here is the Ds. This is 3d1. So you go 1, 2, 3, 4, 5, and of course the answer is it's going to be manganese. That is 3d5. So that's one of the first things you'll have to be able to do is identify it. So where is 5p3, for instance? (5p3). So 2p, 3p, 4p, 5p. So it would be what's it's called? Antimony. Okay. 2, 3, 4, 5. All right, okay. Now we need to go, and so now it wants us to name or draw the electron configuration for nitrogen. So nitrogen's here. It's our 7th element in our periodic table. And so it would be 2p what? And of course it's 2p3. 3 across. Yeah, brilliant. So we're going to name it. Where's the model marker? just about to say unnamed kid. Could even get my other name. It's okay, I found it. So nitrogen, I'm going to write it backwards. We would go 2p3. Okay? But to get there, to get to nitrogen, I need to go back all the way up to hydrogen. Okay? Because I want to start there and direct you there. So if you think about it, it was 2p3. But before I got to 2p3, I would have had to have filled up 2s2. And before I got to 2s2, I would have had to have filled up 1s2. Now, technically speaking, I probably should have written it as 2s1, and then 1s2, and then 1s1. And really, in here, I probably should have had 2p2 and 2p1 if I'm going to stop at every electron. But we don't. We actually abbreviate this. And so what we actually do is we cross this out and we go, look, I'm going to write 1s2, knowing that anybody who looks at this understands that that means that I've filled up those first two in that S shell. And I'm going to look at this and I'm going to just go, well, this 2s2 works the same way. And that if you've got to 2p3, you must have filled in 2p1 and 2p2. And so to a certain extent, I would just write it like that. Now, on Teams, there is a flow diagram that we're going to look at later. And if you're watching this, you're probably going to have to come and ask me about it at school because I don't have a copy of it. But it is sitting there in the middle of Teams that you can work through. So let's say we're going to pick another one. I just like that. I thought it was cool name. Unknown kid. Chlorine. We're going to pick chlorine. Shh. Other unknown kids, stop laughing. So here it is. Here's chlorine in the periodic table. And so if we had to start off with this, well, it's 2p. So this is 3p. And it's 1, 2, 3, 4, 5. So we'd start off by writing 3p5. Now, if you're following along on your periodic table, we would have to go back here and fill in what first? Well, 3s2. Sodium and magnesium, we have to fill in the electrons to get to that point. And then we've got all these, so our 2p6. And then over here, our 2s2. And then follow up by finishing with our 1s2. So basically, filling in the electron levels, electron shells until we get the chlorine. Now, that's fine, but if something gets really, really big, then it can get probably a little bit pointless to be filling in certain aspects of this. So what they'll do is they'll use another abbreviation. So if we look at neon here, it's the noble gas that's above chlorine. And so we would go, well, okay, I'm going to write neon, expecting that everybody understands that these ones are all in neon. Why would we pick a noble gas? Because it's got an octet, it's got a full shell. Okay? And then, so for, if we were going to do chlorine, the only things we would have to write down would be our 3s2 and our 3p5. Because if we have a look, chlorine's not quite at argon. You couldn't write argon -1 or something like that. That made too much sense. No. But we usually go to the noble gases before it. We call both of these abbreviated, but this is probably what most people will be writing these days on their TikToks. You know, things like that. Shh, I didn't mention TikTok. Anyway, so that's more or less what we were talking about with advanced electron configuration. Happy? Okay. Right, next, we're going to talk about the trends in the periodic table. See you then. So next we're going to be talking about trends of the periodic table. And there's 3 trends that I'm going to talk about. The first one is the shrinking of atomic mass as we move across the periodic table. And we'll start with there. So basically, protons and electrons are not the same size. Protons are much bigger than electrons. And the more protons you add, what actually happens. So if I go to the next element across and add another proton, I would also add another electron. But the problem would be is that the mass of these protons would move these two electrons closer in. Okay, shrink them down. And of course, if I add another one then and add another electron, then they're also going to be moving and moving and moving. And so what we actually find is that as we go over here, we get a rather large atomic radius, but then as we move across the table, they shrink. And that is because the protons in the actual nucleus are getting bigger and they're attracting more of the electrons. Yes, very well mimicked. Very well mimicked. Unknown child. And of course, you will see that that is one of the reasons that you get it that I wrote on the board there in the notes that you just copied down. Now, the other thing is, though, is that what also happens is that if we look at these particular things, as we put more and more and more and more and more and more and more of these protons in, what we actually do is we add more electrons in different shells. Now, that means, of course, that we've got 2 here, we've got 8 here, we've got another 8 here, and then we get to the third shell, and then, of course, by the time we get out to, say, our 6th or 7th shell, this electron out here, what's actually happening is that these electrons are doing what we call shielding it from the rest of the nucleus, from the actual protons. So if you think about it, between this electron, if we go to our biggest element, which is like francium, I suppose. Let's have a look at francium. It's not our biggest element, but there's going to be like roughly about 100 or 87, electrons in between this electron and the actual nucleus. And all electrons repel each other because they're negative. We did it in class today, whereas I stood in the corner and I had 2 kids in front of me for the first shell and then 8. And then we had like more and more kids progressively. And I don't say the attraction because that just sounds horrible. Let's just say the control over that kid from the nucleus, that supermassive cool teacher nucleus there, the actual control over that kid, don't give me that look, the control over that kid is a lot less. And so the attraction between this outer electron and the nucleus is much less. And that's why as we move down that periodic table and we move down this side, and I'll just get my little trusty sheet, as we move down here, then the reactivity increases. So how reactive elements happen. If you remember we looked at the Brainiac video, do you remember that one? I know it's a fake, it's okay, guys. The Brainiac video, and then we looked at the guy with the crazy hair, and he kind of had this, so I think it was cesium in a little container. So you can't get rubidium, cesium and francium, or we couldn't get them. And you're not even really allowed now to put in lithium, sodium and potassium in water in front of kids to show the reactivity as you move down. But the reactivity is occurring because of the fact that the outer electron is shielded by the other electrons, and that's why electron shielding is up on the board, and that's why reactivity is up on the board. So yeah. And then electronegativity. So when we talk about looking at, say, your magnesium crack, if you remember we told you that magnesium had these 2 electrons in its outer shell and it kind of very generously gives them to oxygen who needs them. It's not actually that way. Yeah, it's much more that oxygen, once again, its nucleus has 8 big protons. How many is that? 6, 7, 8. Is that 8? 3, 4? No, that's 8. But it doesn't have a lot of electrons around it. And so the shielding from this atom is not a lot. Whereas magnesium has 12 around it. And so these protons are actually attracting magnesium's outer electrons towards it, or basically stealing them. It's like grabbing candy from a baby. And the more electronegative an element is, the more aggressive it is with this. So fluorine, which has one more proton than oxygen, much bigger proton, is the most electronegative element. And I'll show you here. So fluorine here is the most electronegative element in the purate table. So as we go that way, electronegativity begins to increase. So one of the things about it is that electronegativity, and when we start to look at covalency tomorrow, electronegativity affects the location of the electron between two elements that are sharing it. So if we looked at something like oxygen and fluorine, so you had oxygen here and fluorine here, if they were sharing an electron, which they wouldn't, because you would need like two for oxygen and only one for fluorine, but let's say that they're sharing an electron between them. And fluorine is more electronegatively, so negative, so it will actually pull that electron closer to it. So instead of being in the middle there, it actually would be found to be closer to fluorine. That would make this end slightly negative, and that would make this end slightly positive. And we call this polarity. And it does a lot of cool things, like helps trees move water up their trunks, etc., etc. We'll talk about that in a little bit more detail when we study that. Okay, I think that's more or less it. If you want to see more, come see